If you've learned about parabolas, you were probably taught either that parabolas are quadratics or by some definition involving a locus of points equidistant to a directrix and a focus. It's sometimes not taught how these two concepts are the same, so let's quickly walk through that. Suppose you want a directrix y equals negative 1/4 and a focus at 0, 1/4. You want points that are equidistant to both of them, so we can create an equation where the distance to each is the same. The distance to the directrix is just the y value plus 1/4, and we can use a distance formula for the focus, square root of x squared plus y minus 1/4 squared. Now, technically, because this is distance, y plus 1/4 should be an absolute value, but we don't really need that because we'll square both sides immediately to get y squared plus 1/2 y plus 1/16 is equal to x squared plus y squared minus 1/2 y plus 1/16. And after some quick rearrangement, this becomes y equals x squared. Now that we've created the basic parabola, we can fiddle around with the distance between the focus and the directrix to stretch the parabola and translate it however we want. That stuff isn't too interesting, so let's try something else. To get a little more complicated, let's look at satellite dishes. Satellite dishes take the shape of a parabola. This is so that signals perpendicular to the directrix that bounce off the parabola will reflect through the focus. A lot of proofs can be complicated, so let's try to make it as simple as possible. The most difficult math I will use is the derivative, because when the signal hits the parabola, if you zoom in really close, it's helpful to know the equation of this linear tangent, which if we are looking at the point a squared on y equals x squared would be y equals 2ax minus a squared. With that established, we can go on to show why parabolas make good satellite dishes. To do so, we need to show that any line that goes between a point on the parabola and the focus is a reflection of incoming waves. First things first, we want to extend the wave through the parabola to the directrix. The clever trick I'll pull here is drawing the line between the intersection of the directrix with the wave and the focus. Then I'll draw this additional line, the derivative. And if you look at the lines here as I animate it, two of these triangles may look congruent. I'll shade them in red and green. So how can we prove it? Well, they share a side, and by definition of a parabola, their hypotenuses must be the same. For the last step, we can just show the derivative bisects the line I drew earlier. There's a bit of algebra here that we could do to find that they intersect on the x-axis, which is good enough to say it bisects, but we could also look at the equations, say that they're perpendicular, and use the hypotenuse-like congruency, which allows us to use the right angle to have congruent sides, and therefore triangles. I like this a little more because you only need the slope of the derivative, which you can get from the power rule without having to do a bunch of extra algebra. And with that, we have equal angles that show waves reflecting to the focus, and parabolic satellites can work their magic.